So in the previous lecture, we have talked about the uniform convergence of power series of the form an z raised to n. If it has a radius of convergence is r, then this power series is uniformly converging in the all values inside this neighborhood, or I can say minus r to r. If your z is a real number, otherwise it is mod z is less than r. Then if it is uniformly convergence, and according to that we can say that a term by term differentiation of the power series is possible, and term by term integration is also possible. So that also we have proved in the previous lecture. The next one we have did it is the identity theorem for power series, which tells you that summation an z raised to n is same as summation bn z raised to n. That will implies that an is equal to bn for every n. This is known as identity theorem. If the summation of an and summation of bn, both of them have radius of convergence is r, under the radius of convergence, or whatever the interval of convergence is there. If in that interval of convergence these two power series are equal, then that means each component is equal. Here in this lecture, we are talking about the power series, convergence of power series at the boundary of this radius of convergence. That means at point z is equal to r. The what we have proved, it is inside any point you can consider inside the interval, then this power series is uniformly convergent. Then the question arises, what will happen at the boundary of that interval? So this theorem, which tells you the convergence of a power series at the boundary point, is known as the Abel's limit theorem. So in this lecture, we will discuss about the Abel's limit theorem, which gives you the convergence at the end point, or I can say at the boundary of the interval of convergence. So let us take as a statement fx is represented as its power series like an x raised to n be a power series with radius of convergence is 1. Here we are discussing this theorem with radius of convergence is 1. If the radius of convergence is r, same proof will follow, just replacing 1 by r, and similar type of adjustments we have to do. And if the series converges at 1, that means x is equal to 1, that means summation of an is convergent, then prove that a limit of x tends to 1 minus fx is equal to f of 1. Ultimately, we are saying that this is limit x tends to 1 minus summation an x raised to n is summation of an. And if the series converges at x is equal to minus 1, then prove that a limit of x tends to minus 1 plus fx is equal to f of minus 1. This is equivalent to write down as limit x tends to minus 1 plus summation an x raised to n is same as summation minus 1 raised to n into an. Now here, why we have taken this left hand limit and here it is right hand limit, because you know that the radius of convergence is 1. So the interval of convergence is minus 1 to 1. So that is the interval of convergence of this power series. And the question is, what will happen at the end points? So it says that if the series is convergent at, that means the summation of an is convergent, then you can talk about the convergence at the end point. And here it is, we have taken it is a left hand limit because we are approaching from this side. And here we are approaching from this side for minus 1. So that's why it is a right hand limit and left hand limit we have talked here. So to prove this one, let us consider Sn is equal to summation k running from 0 to n ak. That means it is a partial sum of ak. And this partial sum is convergent because we have assumed that the series is converged at x is equal to 1. That means summation of an is convergent. So this partial sum Sn is convergent. Now let us looking at what will be this Sn minus 1. The Sn we know that is the sum of first n term, that is summation k running from 0 to n ak. And Sn minus 1 is a sum of first n minus 1 term. And this is this. So if I can expand this one, the first summation is a0 a1 up to an, and the second summation is a0 plus a1 up to an minus 1. And you can observe that this a0 is cancelled out, a1 is cancelled out with this terms, and an minus 1 is cancelled with the previous term to that. So only the quantity is left is an. So ultimately what we got is an is equal to Sn minus 1. So from this what we can say is the summation of an x raised to n running from 0 to infinity. If I substitute this value of an here, then this is summation n running from 0 to infinity Sn minus 1 x raised to n. And if we can separate this out, then this will be summation n running from 0 to infinity Sn x raised to n minus summation n running from 0 to infinity Sn minus 1 x raised to n. When I write Sn minus 1 for n equal to 0, we take S minus 1 is 0. That is the first term that we can consider, otherwise there is no meaning of that quantity. So we have considered that term which having the, this is I don't want actually to infinity. I want that it has to be from some finite quantity. So for that I'll just take it as to m. The summation is running from 0 to m. And this is equal to, if you can change the index here, that is summation n running from 0 to m Sn s raised to n minus summation n running from 1 to m Sn minus 1 x raised to n. And here if I change the index by replacing n minus 1 with n in the second summation, then that will be n running from 0 to m Sn x raised to n minus summation n running from, now when I replace n minus 1 to n, when n starts with 1, this new n will start with 0 and the limit is m, so the new m will start with m minus 1. This is Sn and x raised to n plus 1 we can have. So here we combine this two summation now. The mth term from the first summation I can make it separate. So this we can now rewrite as summation n running from 0 to m minus 1. Sn is common out from this two quantity and xn minus xn plus 1 is there, and plus the mth term from the first summation, that is Sm x power Sm, is common out. You just see, observe that what is the common quantity from this two, that is x power n is common. So what we can left with, it is 1 minus x is left from this, and inside we will have n running from m minus 1 Sn x raised to n plus Sm x power m. I call this statement as 1. On the other side we have summation n running from 0 to m an x power n. So I will call this statement as statement number 1. Now as we know, this Sm is a bounded. Why? Because it is a conversion. So it is conversion, so it will be bounded. And this x power m, as your x is between minus 1 and 1, because the radius of conversions is 1. So it is between minus 1 and 1. So what we can say about the limit of this quantity, that is Sm into x power m. So we'll write that as Sm is, why Sm is conversion? Because the summation of an is conversion and Sm is the partial sum of this summation of an. So that's why it is conversion. That is our, we have assumed. So this is conversion, the Sn is bounded. So therefore there exists some m greater than or equal to 0, mode of Sm is less than or equal to m. And if I multiply this x power m, this is less than or equal to m into x power m. If I take the limit n tends to infinity, this is mode Sn x Sm x raised to m tends to infinity. This is limit of m tends to infinity, capital M into x power m, and this will tends to 0 as your x is belongs to minus 1 and 1. So this quantity is 0, this is already greater than or equal to 0. So ultimately the conclusion made out of this is, therefore a limit of n tends to infinity Sm x power m is 0. M tends to infinity. So what we'll do is we'll take a limit both sides into the equation 1 as m tends to infinity. So now for 0 less than x less than 1, from equation 1 we get a limit of m tends to infinity, summation n running from 0 to m an x raised to n. Here it is 1 minus x, which is independent of m, so I may write down it is outside the limit. Limit m tends to infinity, n running from 0 to m minus 1 Sn x raised to n plus a limit n tends to infinity, m tends to infinity, Sm x power m. We know that this will tends to 0, and this quantity is now become 0 to infinity, an x raised to n equal to 1 minus x into n running from 0 to infinity, because m is tend to infinity, m minus 1 is tending to So we'll have this, and what is this function on the right hand side? That is given as fx. So we got fx is equal to 1 minus x summation n running from 0 to infinity Sn x raised to n. We call this as a statement number 2. Okay, because you can see that into the given series, the fx is summation of an x power n. Now let us take S is the summation k running from 0 to infinity, because this summation of ak is convergent. So let's say it converges to S, and we know that for mod x is less than 1, summation of x power n running from 0 to infinity, will be 1 upon 1 minus x. This is a geometric series. So using that geometric series, we can write down the sum of the geometric series is 1 upon 1 minus x if your x is between minus 1 and 1. So from this, what we can got, it is 1 minus x into the summation equal to 1. If I multiply 1 minus x both sides, and I have called this as the 3. Now from 2, ultimately what we have to prove? We have to prove this limit of this fx is this s, that is summation of, so limit of what is fx is this summation of an x power n. What is our objective is limit x tends to 1 equal to summation of an. That is our objective. So this is our goal, that limit of x tends to 1 minus summation of an x raised to n is summation of an, and this summation of an I have taken as s. So ultimately I need to find out what is the limit of this fx at x tends to 1, as at x tends to 1. So we'll see what is the difference between these two, fx minus s. If I can prove that is less than epsilon, then it is fine, as x minus 1 is less than delta, or as x tends to 1 minus. If we can do that, then it will be fine. So that is our objective is. So let us see what is fx minus s. So now, what is this fx minus s? I am not taking the modulus here, so we'll take modulus later on. So what is this fx? From equation 2, what we have taken fx is this 1 minus x into summation of Sn x raised to n. So that will be right. And what is this s? We have write as s into 1. That is summation of this. And 1, instead of 1, we'll use the equation 3. So this is as it is, 1 minus x summation Sn x raised to n running from 0 to infinity, minus s into 1 minus x into summation n running from 0 to infinity x raised to n. You may just observe that 1 minus x is common out from this 2. So this we can rewrite as 1 minus x summation n running from 0 to infinity. That summation I am combining both these terms. Here the quantity is left is Sn x raised to n. Here the quantity is left is s x raised to n. So I may write down that as Sn minus s x raised to n. X raised to n is common. I may call this as equation number 4. Now since summation of an converges to s, what will happen if I take the limit? here limit x tends to 1, we have to see what is the summation, how the summation of Sn minus S is behaved. What is Sn is the partial sum of An, and what is S is the convergence of the summation of A. Obviously, these two things is converged, means tends to 0. But for that, since this we have, for given epsilon greater than 0, there exists n0 belongs to n such that mode of Sn minus S is less than epsilon. For every n greater than or equal to n0. So whenever n0 bigger than this will be less than or equal to less than epsilon. And what we'll do for all the values, so we have now the value of n, that means in this summation, we start with 0 to infinity. So after n0, this is tending to infinity. So if I split this summation into two parts, the one is start with 0 to n0, another one is start with n0 to infinity. Then we have already achieved that from n0 to infinity, this summation will tends to 0. What will happen now for n0, 0 to n0? And in the 0 to n0, this Sn minus S is bounded. Okay. So what we can say is, therefore, there exists some m greater than 0, Sn minus S is less than m for every n. We can say this. Now, from 4 and your x is between 0 and 1, let us see what is fx minus s. So I will taking the modulus, this is your fx minus s. Taking the modulus here, so if I can take mod both sides here, the mode of this 1 minus x, the value of x is less than 1, so 1 minus x is always positive, so that I can write down outside, and then it is modulus, and this summation I may split into two summations. The one is running from 0 to n0, Sn minus S x power n, and another one is n0 to infinity, Sn minus x power n. And then by triangle inequality, this 1 minus x as it is, this is summation n running from 0 to infinity, mode of Sn minus S x power n, not n0 to infinity, it is n0, plus n0 to infinity, mode of Sn minus x power n. Now inside this 0 to n0, this is less than m I can write, and this m is independent of n, so I may write down that is outside the summation, so that is less than or equal to 1 minus x into m summation n running from 0 to n0 x to the power n, plus Sn minus S is due to this Sn minus S is less than epsilon for every n greater than or equal to n0. So in this one it is less than epsilon. So I may write this is epsilon into summation n running from n0 to infinity. Or this is n0 I have started, so you can write n0 plus 1 here. No problem. Okay. Here also you can write n0 plus 1. This is less than epsilon x power n. But this I am adding some more terms here. And here this is a geometry, finite geometric progression or sum. So that is 1 plus x square up to x power n0 is there. So that is less than, also that is equal to 1 minus x into m into this quantity. As you know that it is the summation is, we can write down 1 minus x0 and 0 plus 1 upon 1 minus x. So as per that we can write down this, and this quantity I'm adding some more terms here. So instead of equal to, I may write down this is less than or equal to epsilon into 1 minus x. Now I'm multiplying this 1 minus x to both of them. Summation n running from 0 to infinity x power n. And hence what we got, this 1 minus x is cancel out. So this is equal to m into 1 minus x power n 0 plus 1 plus epsilon into 1 minus x into 1 upon 1 minus x, because the summation of x power n is 1 upon 1 minus x, and this 1 minus x will get cancelled. This is less than epsilon, and this will tends to 0 as x tends to 1. So I can say this will tends to 0 plus epsilon, and epsilon is arbitrary as x tends to 1 minus. So ultimately what we achieve, a limit x tends to 1 minus fx will be s, and s is a summation of an. Ultimately what we got is limit of x tends to 1 minus fx minus s is less than or equal to epsilon. This is actually we got from this. But epsilon is arbitrary, so we can say that this is equal to 0, so this will be convergent. And similarly one can prove the other part, that is for the other side, a limit of x tends to minus 1 plus fx is equal to summation minus 1 raised to n into a. So in the other part also we can do the similar way. So this is a proof of Abel's limit theorem, which talks about the convergence of power series at the boundary of the radius of interval of convergence. If you have any questions regarding this, you can ask.